All right, lab 2, motion of a falling object. Let's get into it. So a little background and information about the experiment. So in this experiment, we're just observing a falling object. In my case, I picked a soccer ball. And then using tracker, we are tracking the position of the object as it falls, and then comparing this to two computational models that we construct, one with drag and one without drag. And so the basis of this experiment revolves around Newton's second law. We already know the equation Vf equals Vi plus F net over m times delta t. That's nothing new. And it's important to keep in mind we are focusing on the y component of the F net vector because we were only interested in the downward motion, linear downward motion. So we can ignore the x and z components. And in our experiment, the force of drag is equal to the coefficient of drag times velocity squared. And our force of the weight will just be gravity times the mass. In this case, it's 0.45 kilograms. After that, using that information, we can use every time we use a VF, we can put it into the equation, the RF plus RI equals VF times delta T to calculate the new position. We already know how to do this. This is nothing new. All right, so I'll quickly go over both computational models. So you can pause the screen if you want to read the whole model, but basically the key takeaway here is that the net force is equal to only the weight, obviously downwards because that's the way that gravity faces. And so gravity is the only force acting on the soccer ball in this model. So F net will just be the gravity times the ball mass. And as you can see, our velocity against time graph is linear. All right, so moving on to the computational model with drag. As you can see, it is basically the same except for the net force. So I wrote minus a vector here, but the key takeaway is that this will be the net force now is equal to the weight of the ball, so the gravity times the mass, plus the drag that we create. And so in this case, we have our proportionality constant times our velocity squared. And as you can see, our velocity versus time graph is not linear, although we have a small proportionality constant, so it looks pretty linear. However, it is not fully linear. It actually will slope off towards the end because of the drag. Now to the most important part of the lab, we have to compare all of these three models. So as you can see, we put them all into one position versus time chart. And as you can see, I've labeled the model with the drag, without the drag, and the observation from tracker. And basically the key takeaways from this are that the model without drag falls a greater distance than the observed tracker model. This tells us that other than weight, there's another force acting on our soccer ball that we dropped. This will be the force of drag. So as you can see, our model with the drag is pretty good. It's a pretty good approximation at the very start and at the very end. However, the model over approximates throughout the middle. Why is this? This could be due to camera distortion, the human error from clicking at the center of the mass of the ball. That could be a little off. And then it's also indoors. There was really not that much air resistance, and the height is not tall enough. I'll elaborate on this later. So we've come to the conclusion that obviously there's drag affecting the ball because the observed model from the tracker and the computational model without drag did not line up. So basically, do any of our models predict the terminal velocity? What exactly is a terminal velocity to begin with? So a terminal velocity is when the net force will equal 0. So this means that there will not be an increase in velocity, it will just stay the constant velocity. And the short answer is no. And this is because we have a small proportionality constant, and that's why our model looks more linear due to the equation F net equals m times g minus b times vel squared. The distance that we dropped it from is not tall enough to observe a terminal velocity. And in order to get a better terminal velocity, we would have to drop it from a taller height. So what if we did reach a terminal velocity? So first I had to model this, and in order to model this, I used the same computational model, like on the Glow script, and I changed we had a small coefficient of drag, so I changed it to 1 instead, and then I increased the time to 2 seconds. And so I created two models where one, the initial velocity was 0, and then for the other one, the initial velocity was -10 in the y direction, -10 meters per second in the y direction. And I compared both of them, and as you can see the results here, the velocity actually does reach the same terminal velocity, and in this case it's negative 2.1. But that just goes to show that no matter the initial velocity, the terminal velocity will be reached like eventually. So I thought it was pretty interesting, and thank you for listening to my lab.